In this video, we're going to dive into weak acids and ice tables. Weak acids are different from strong acids, and in that they don't break apart completely. And to find the pH of such a solution, it requires an ice table. So in this video, we're really going to connect acids and bases to equilibrium. First, let's talk about strong acids, even though this is mainly about weak acids. Finding the pH of a strong acid is really easy. If 100% of the acid molecule ionizes, then the concentration of hydrogen at equilibrium is also going to be the same as the initial concentration of the acid. To find the pH, simply take the negative log base 10 of the initial acid concentration. Now, how do you know you have a strong acid? Either the problem is going to tell you directly, it'll say, what is the pH of this substance, a strong acid? Or there are 7 strong acids. Icyl broso no clo is the mnemonic that I remember. HI, hydroiodic, HCl, hydrochloric, HBr, hydrobromic, H2SO4, sulfuric, HNO3, nitric, HClO3, chloric, and HClO4, perchloric. Here's an example. There we go. Here's an example. Let's say we're given the task of finding the pH of a solution of 0.1 molar nitric acid, HNO3. And the problem even tells you it's a strong acid. To do this one, you would simply take on your calculator the negative log of 0.10. Hit enter, and you should get 1. Here's another easy one. What's the pH of a solution of 0.025 molar HBr, hydrobromic acid, a strong acid? Again, we're simply going to take the negative log of the concentration that they give us, negative log 0.025. And if you round it to 2 sig figs, you'd get 1.6. Those are the easy ones. Strong acids, very straightforward. Weak acids, a little tougher. To find the pH of a weak acid, we're going to start by writing the acid dissociation equation and the equilibrium expression. We're going to set up an ice table. The problem will always give you enough information to set up an ice table. Then we're going to substitute equilibrium concentrations into the equilibrium expression, and we're going to solve for whatever it asks. Now, here's a crazy thing. If X is added to or subtracted from something, when you're doing your math, you can ignore it. The reason for that is the Ka values for weak acids are all quite small. They're on the order, the biggest of the Ka values that you would see are on the order of 1 times 10 to the negative second. But then they go much, much smaller, all the way down to like 1 times 10 to the negative 10th. So the range of values that we're talking about is so incredibly small that the value for X that you calculate is going to be very small as well. If you subtract a very small number from a much larger number, it doesn't change significantly the value of that larger number. And so we can approximate the value of adding X or subtracting X by just ignoring it, provided that we know that the value of X would be quite small. I'll show you what I mean with this sample problem. Let's say we're asked to calculate the pH of a 1 molar solution of HF. Now, HF is not one of the 7 strong acids. So you're not going to be able to simply take negative log of 1. They also give you a hint. The Ka value for HF is 7.2 times 10 to the negative 4th. Whenever the Ka value is some small number like that one, it's going to be a weak acid. The Ka values for strong acids are super high. They're like much greater than 1. They approach infinity, in fact. So if you've got a Ka value that's much less than 1, then you've got a weak acid on your hands. Okay. if we were to write the acid dissociation equation, it would look something like this. HF yields H plus and F minus. By this point, we should be good at writing acid dissociation equations. The equilibrium expression, we would take, and we'll get to that in a moment, but we would take the product concentrations multiplied together, divided by the reactant concentration HF. So H plus concentration times F minus, all over the HF concentration. Now, you might think, how are we going to set up an ice table? They only told us one thing. They say the pH of a 1 molar solution of HF, or calculate pH of a 1 molar solution of HF, and they give us a Ka value. They didn't give us any other initial concentrations, and they didn't give us any final concentrations. What are we going to do here? Students, remember this. If they don't mention a substance being present in the reaction vessel, then you should assume it's not there initially. So if we're looking at this acid dissociation equation and we say, okay, HF, what's its concentration? 1 molar. They told us that one. But H plus, they didn't give us any information. It's 0. F minus, same thing. They didn't give us any initial information about that. It's 0. So in the initial line of the ice table, it's 1, 0, and 0. To which side do we shift? Actually always for us, and especially in weak acid cases, it's always going to be a shift right. Notice that the coefficients are all 1, so you don't need to worry about, is the coefficient 2, and should I put a 2 in front of the x? No, it's all 1. So in the change line of the ice table, minus x for the HF, plus x for H, plus x for F minus. And then, of course, in the equilibrium line, we're simply adding together the initial and the changes. So 1 minus x for HF, simply x for the H, and simply x for the F minus. Okay, we've got at least an ice table fleshed out. Where do we go from here? Let's go to the equilibrium expression. The product concentrations multiplied together, H plus times F minus, all divided by HF. We know that the concentration of H was X. The concentration of F minus was also X. So if you multiply those two together, you would get X squared. And the HF was 1.00 minus X. Okay, now what information did they give us? If X is added to or subtracted from something, you get to ignore that. Remember that helpful hint? So in this expression, 1.00 minus X simplifies to simply 1.00. Isn't that nice? Now you might say, that seems wrong mathematically. Students, remember this, the value for X is negligible. So 1 minus something super small is still roughly 1. Now we plug in 7.2 times 10 to the negative 4th is the Ka value. We multiply both sides by 1. And that works out to be x squared equal to 7.2 10 to the negative 4th. Take the square root of both sides. And x, the square root of 7.2 times 10 to the negative 4th, is equal to 0.027. So now we've got a value for x. We greatly simplified the equation by ignoring the minus x. And students, would you agree that 0.027 is quite a bit smaller than 1? If you were to take 1 minus 0.027, you'd get like 0.97. That's pretty darn close to 1. Going back to the ice table, I specifically want you to focus on the concentration of H plus at equilibrium, because that's what allows us to determine pH. In the ice table, the concentration of H is X, and we now know that value. It's 0.027. So now, finally, we're at a point like the strong acid problems where we've got our H concentration. We'll simply take the negative log and get pH. So we're going to take negative log of 0.027 And we get 1.57 for our final answer. Ooh, good luck, students. This is a fun one.